So my name is Paul Gazzillo. I'm an associate professor here. In addition to teaching, I also do research, mostly in the area of software engineering, but also in programming languages, program analysis, security. So take a look at my webpage if you're interested in research or interested in what else I work on. But in this class, we're going to be studying system software. So any class you take, you should probably think, how is this going to be useful? Why should I take this? Why are the school offering it to me? So the main reason, in my view, to take system software is to know your tools. So this picture is from Isaac Newton. Who knows who Isaac Newton is? A lot of people didn't know that semester, which is a little troubling. So what did Isaac Newton do? Any takers? Yeah. Yeah, so he modeled gravity, made a mathematical model. Yeah, apparently he did. He invented calculus in order to make his models of gravity. Yeah, so he did this kind of core scientific work that really kind of ushered in the scientific revolution. But he didn't just do things on paper. He also built tools, because in science you need physical tools, you need to do observations. And this is a page from his notebook where he was learning about how to grind his own lenses. He did observations, astronomical observations, and to do that, you need tools to do that. You need observations, you need physical tools. So I see this as the same thing in computing. There's lots and lots of cool theoretical work in computer science, lots of algorithmic work, but I'm guessing a lot of you want to be engineers, software engineers, building stuff, building systems. And to do that, it's really good to get your hands dirty and know your tools. So you might have heard this proverb: a poor workman blames his tools. And the beauty in computer science is that our tools are software, largely, and we can actually modify those tools. We can tweak those tools. We can build our own tools, just like carpenters do, or Newton did with building lenses. A couple other proverbs. So tools are made for man, not man for tools. So if you've ever sat at your computer and said, why is this so slow, or this program is not working the way it's supposed to, well, you have control over this machine. You have complete control over it, almost entirely, at least above the hardware level. And so if you know your tools, they'll work for you. You don't have to be subject to the way your tools work. You can modify them at will. You can use them to build large systems. And I thought I made up this quote, but I didn't. So Aldous Huxley, Thomas Merton said this: technology is made for man, not man for technology. So sort of have the view that I control the software, I control the machine, and you'll be much more powerful as a software engineer and a system builder with that philosophy. And of course, quote from my dad: don't use your hands, use a tool. So instead of doing things manually, the computer can automate things for you in pretty incredible ways. And when you learn those tools, you'll be much, much faster, you'll be much more productive. So there's like kind of a rule of thumb that great programmers and good programmers, great programmers are like 10 times more productive than good programmers. And part of that is knowing your tools. Okay, so to that end, to helping you know your tools and become better software engineers, better computational thinkers, there's two main goals that I have in this course. One is to actually use system software. So if you've done Intro to C, you've done other programming courses, you probably used some pretty basic tools. You may not have use the command line very much. And two, to actually build system software. You can see how some of these tools that you use all the time, maybe unknowingly, how they're actually built under the hood. And there's some pretty cool history and cool technology that goes into making these system tools. Okay, so what is system software? So it's really hard to find a good definition of this. You can kind of go on Wikipedia, you can search. So the definition I'm going to use, that's, I think, broad enough and specific enough for this course, is that it's the bridge between the operating system kernel, so that low-level piece of software that you all kind of have to install first to use your machine. You don't have to, but we all do. And your applications. So applications are like your web browser, your email, and there's this very large set of software in between that bridges this gap, that makes application development possible and makes possible all, downloading cat pictures and sending memes on the internet. There's a huge amount of software in there that's doing the heavy lifting for these application developers. So here's a picture of what that looks like. Here at the bottom, we've got our hardware. Hopefully you learned about this at some point. I know we're not electrical engineers, but You have your RAM, you have your chip, you have your peripherals, you have your motherboard, and at the very top, those are all the things that consumers use. People who aren't even computer programmers or software developers, they have no problem using these applications. In between, that's the system software. So these are things like compilers, language tools, Python interpreters, editors for your software, integrated development environments, IDEs, libraries. If you ever used printf, you're using a library that somebody else wrote for you to make printf work properly. And also programming environments, and this is really important for productivity. So there are lots and lots of tools for helping you be a fast and reliable engineer. Things like version control. Who's used version control before? Like Git. Oh, okay, that's pretty good. A little like 30%. Make. Anyone ever use Make or a build system? Okay, many fewer. So if you want to go out and be a professional software engineer, you're most likely going to be working on an already built system, and there's probably going to be lots and lots of code, written scaffolding code that actually you have to sort of understand and use. And Make is one of the original versions of this kind of scaffolding tools. Okay, so for the course goals, number one, using system software. And I'm going to introduce you to a couple of standard open source versions of these, but if you go out into the kind of real world, there will be versions of this in any operating system or any development environment you have. But we're going to learn the command line, the bash, specifically the bash command line. But we're going to learn the command line. Who here uses the command line regularly? That's pretty good. About a third. Maybe that's the same third that uses version control. Who has never used the command line and is willing to raise their hand? Okay, so everyone's used the command line. That's good. So the reason to get comfortable with the command line is it opens you up to the full power of your operating system. So applications are typically written for very specific purposes, but when you use the command line, you not only can use the full power of the operating system, but there's a huge amount of software, including system software, that's written only for the command line. It's a very, very simple interface, and so there's a huge amount of tooling that you can use for that. You can also do a huge amount of automation that's much easier to do on the command line than having to write some bespoke program or Python script. And I'll show you a little bit of this. Could be a whole course on just using the command line, but I'll show you some useful techniques for doing automation on the command line. So we'll talk about it later, but the Unix philosophy is that you build software that does one simple single purpose, and then like Lego blocks, you can combine these together to build sophisticated systems without even writing a single line of C code. You can just cobble together existing tools. So that's kind of the Unix philosophy. We'll see that a little bit in this class. So command line is definitely, we're going to be using the command line. We're going to use it on Eustace. We're also going to be using version control. So for those of you who've never used version control, this is de facto standard in pretty much any software development shop. Even people use it for documentation and other purposes. It's made for software development, but you'll almost certainly be dealing with version control. So it's good to have early exposure to this. And I'm going to give you very, very gentle introductions, very easy introduction to this, but you will have to use it for submitting your project, so you have motivation to actually learn it. And version control is almost essential for building large software collaboratively. If you've ever cut and pasted code or copied entire C files to give to your friends to work on, you know how tricky it is to try to have multiple people working on source code, and this is what version control solves, and it does a really good job at it. But even as an individual, so for instance, for my individual projects, I use version control anyway, just to track the changes to my code and organize adding features, making bug fixes, and maybe not so much in this class, but you'll see over time that version control is an essential tool for doing reliable, large-scale software engineering. I also want to make sure everyone understands the file system. So modern operating systems kind of give you a lot of distance between the operating systems. If you use Mac, you have the Finder, you may use Search, and so I think people less and less are really understanding how the underlying operating system works, or underlying file system works. There's too many people who, you download a file or you put a file somewhere and you're like, all right, where is it? Where did it go? How do I find it? And so we'll learn kind of the basics of the file system, and it's one of the core features of the operating system, so we write our system software. will learn about how things like the copy function or move or other file operations are actually implemented, how those commands are actually implemented that we kind of use and take for granted. But I want to say that if you don't know about this yet, that's okay. This is engineering design. Some people designed this file system, and it's not some law of nature. So if you haven't learned it before, you may be unfamiliar with it. And lastly, familiarity. I want to make sure everyone is familiar with development tool chains. And we're going to use the GNU Linux tools for this. The GCC, you've probably used this already, but we're going to use Make, GCC, and we're going to kind of go through a really basic, classic development tool chain. If you're just writing C code and you've never thought about build systems before, then this will give you a little introduction to how professional software development is done. So for instance, take something like the Linux kernel. It's about 20 million lines of code. They've got 200,000 lines just in their build system. So these things can be substantial scaffolding in large-scale professional software. And all this is going to be on the command line, but those knowledge that you learn about these systems translates to IDEs. Whereas if you just use an IDE all the time, you learn that IDE, but you may not be able to easily transition to other graphical environments or other build systems. So I'm going to try to give you kind of the fundamentals and the classic development tool chains. All right, so that's the first goal. The second goal is to actually build system software. So we're going to build a few pieces of system software using kind of classic the classic Unix-style development. We're going to do a file handling system software. We'll do things like reading and writing files, copying files, moving files, working with the file system, and process management. So process management is, if you've ever wondered why you can browse the internet while listening to music, well, the operating system is designed to allow multitasking, to allow multiple things to run at the same time. Even if you have one CPU, it looks like you have many things running. That's the process abstraction. We're going to work with that as well. We're going to work with the kind of original Unix APIs for doing that. And we're going to do some work with compilers. We're going to see how high-level languages get translated to machine code and see how those integrate with your system. The compiler and the operating system work together along with your programming environment to allow for large-scale, easier software development than just like programming on bare metal in assembly. And kind of in the background, my kind of ulterior motive here is to just make everybody a better programmer. And I think by knowing your tools and having this experience getting your hands dirty with system building, I think that will make all of you a better programmer. All right, any questions, any thoughts so far on goals of the course? Kind of clear, makes sense? Motivated to do some system software, I hope? All right, so let me give you a little allegory here, the classic tortoise and the hare. Anyone not familiar with the tortoise and the hare? I think everybody knows this story. Okay, so the tortoise and the hare, two animals, they're each given the same challenging programming project, like the one you're going to find in this class. Some of the programming projects are not easy. So what does the hare do? The hare just starts coding immediately. And I'm sure many of you have this experience. Maybe they waited the day before and they're like, all right, I got to code all night. What does the tortoise do? Well, they don't code at all. They start writing comments. They start organizing and planning what they're going to do, and they start writing test cases. How do you write test cases? You don't have a program. Well, the tortoise does it. And the hare goes so fast that he finishes before the tortoise even starts programming. So he's way ahead, right? But this is where the real work begins. The actual coding part, once you've learned the basics of like programming languages, it's not that hard to just spit out code. Here's where the real work begins. So the professor or someone, their employer, gives them a test case. And what happens? It's going to break. Who's ever written something more than 50 lines that had 0 bugs the very first time you wrote it? Anyone ever do that? I don't think I have. You have? Okay, good on you. What about 200 lines? Kind of, I think? Okay, so no. So no. So if you're not sure if it works right, probably it had bugs. So anyway, it breaks the code. And what does the hare do? Well, the hare just starts guessing and changing code that they think might be broken. And they fix it, but now other test cases are breaking. And maybe they've even broken things that they thought they fixed before. So if they're lucky, all the given test cases might work, but they still get a bad grade, because I'm not going to give you all the test cases. You're going to have secret test cases. And in the real world, there's going to be things you may not have thought of that your client or your employer expects out of your software that doesn't have a test case, because you or your test engineers are the ones making the test cases, maybe you miss something. But the tortoise, well, the hare is freaking out and trying to just throw everything at the wall to get their code to work. They start by breaking the problem they have to solve down into small pieces, because it's easier to solve smaller problems, easier problems. And he writes some simple examples to illustrate the problem. He takes an easy part of the problem and writes comments about what the code should do. And only then, little by little, does he do line by line pieces of code, testing all along the way. Doesn't move on to 100 lines before the first couple of lines are actually tested. So when I start writing a piece of code, I write hello world, because I'm almost positive I can get that right. I want something working after every time I work on that code. I don't want to leave potentially broken code. So the tortoise makes sure simple things are working before moving on. He doesn't take for granted at all that the code just works. He doesn't make any assumptions about his code. He tests objectively and has objective reasons and planning and comments to have high assurance that his code actually works. Because he knows that debugging is really hard, especially when you have lots of different bugs. It's really, really hard. And this is kind of the crux of why good and great programmers are 10 times different. Because once you have a few hundred lines of code, it's much, much harder to debug 200 lines of code than it is, say, 10 lines of code. So if you're only working on 10 lines of code at a time, much easier to debug that. So the tortoise took a lot longer to actually get some code out, but when he got there, the code was easier to write, it was much less likely to have bugs, and even when there were bugs, they were easier to find, because he was only working on a small part of the code. Okay, so anyway, I'm kind of beating a dead horse here, but while the hare felt like they were coding really fast, the tortoise was just gradually writing tests, commenting, writing a few lines of carefully thought out code at a time. And when he runs the tests, nearly all of them pass, because he's already doing testing. And for the ones that don't, he just uses some good debugging strategies to figure them out. And when encountering unknown tests, because he already was thinking about the correctness of the code, he's very likely to get a good grade. So kind of big takeaway here for being a good programmer is be the tortoise when you're coding. It can work, so I should say there are absolutely times to hack code together, like small scripts and do some hacking. But in the professional world, when you're working on large or maybe mission critical or life critical systems, slow and steady kills fewer people, basically. Wins the race. You have better software and less dangerous software if you're actually working on life critical stuff. All right, questions, thoughts? So resist the temptation to try to program everything all at once, and don't feel like you're going slow if you've only written a few lines of code. Okay, so some tips on how to be the tortoise, and we'll go over these during the class, during the semester, and we'll give you the actual tools for testing and building software. So first is know your programming language, and this is why learning compilers, or at least learning programming language, is so important. This is know your tools. So if you know your programming language really well, you won't have to guess at what it's doing. When you write code, you can know what it's going to do, and when you go to debug, you can run in your head what that program is actually doing instead of what you think it's doing. So know your programming environment. This is why I teach about build automation and programming environments, because this will make you really fast. If it takes you 5 or 10 minutes to switch between running a test, editing code, and rerunning it, that's going to slow you down. So if you can really, really quickly test, compile, you'll just be faster, just because that overhead is reduced. Break the problem down before coding. Use abstractions like functions and objects, which you'll learn about here in your course. This helps you organize your code. So you don't have to use functions. You don't have to use objects. You could just write everything in assembly. But these are to help you as the programmer organize your code. This is really important. This is the is it plugged in? So you might have seen like funny tech support videos or memes about tech support. Somebody calls and it's like, oh, the computer's not plugged in. Be lazy. Always check the easy thing first. So make sure simple stuff works. Don't take for granted that even adding 2 numbers works correctly. Test it. Write your own tests and save them. Don't have one file where you change the file and change the test, because you've just wasted valuable work that you did. So save each test that you did before, and then that'll make sure you don't have any regressions. It's called regression testing. All right, develop good debugging skills, and I'll talk about this a little bit today as well. I'll give you a little schema for debugging. All right, so this is not just me. This is kind of knowledge from great programmers throughout history. Who's ever heard of Brian Kernighan? Nobody. Okay. So he was one of the sort of original sort of AT&T Unix guys. He co-wrote the book on C programming, like the original book on C programming, because his colleague developed the language at AT&T in like the 70s, 60s, and 70s. And so he has a famous quote: "Everybody knows that debugging is twice as hard as writing a program. So if you're as clever as you can be when you write it, how can you ever debug it?" So it's a little tongue-in-cheek, but the idea is that be really simple-minded when you code. Make it easy on yourself when you code, because debugging is really hard. So if you write complex, convoluted code, you're going to have a really hard time debugging it. All right, so I've been using this term bug a lot, but we should probably define it. What is a bug? What do you guys think a bug is in a program? Yeah? A problem in the program. Okay, problem in the program.
And unexpected behavior.
Unexpected behavior, expected by who?
The developer usually.
The developer, okay. So we've got two answers here. We have the program has a problem, and the developer does not expect what the program is going to do. So what I think a program is not, sorry to throw you under the bus, but is that the program does something wrong. Because almost always the case, the machine is doing exactly what it's told to do. It's a machine, and it has a well-defined definition, and if you write code, it's going to follow it and do exactly what it's supposed to do. So if you have a null pointer error, and you get this like seg fault, the machine is doing exactly what it's supposed to do. If you dereference 0, and then the hardware traps and does a seg fault, that's exactly what it was designed to do. So my view, my kind of opinionated view, is that's not actually a bug. The problem is that the program is doing what we think it shouldn't be doing. So it's a violation of our expectations. So the program does something you don't expect it to do. And so what it really is just a gap between what we think reality is and what the program is actually doing. And that's really hard in the scientific world, because or the real world, because we have no control over the physical world. But the machine we do have control over. We can actually change that code. So the first step in any debugging is not to try to fix anything. It's to try to understand why I think the program is doing something different when it's actually not doing that at all, what I think it's doing. Okay, so that leads us to a very simple schema for doing debugging. And I'll give you a 3-step schema for debugging. So first is not to look at the code. Just like when you're programming, don't look at the code. First, you start with your test case. So in order to even know you have a problem, you need some observation. You need some way to show that you have a problem. And so presumably you have a test case. If you don't have a test case, then how do you know? It's like a tree falls in the woods and no one's around to hear it. How do you know your program has a bug? Well, it has a bug because it broke. You wrote you tried to use it and it didn't work the way you want. So the first thing to do is to take your test case and try to narrow it down as much as possible. So if it's a complicated test case, narrow it down as far as you can until the bug is still there, but not gone. You might change your test case and then the bug is gone, but narrow it down so it's the simplest thing, smallest version of your test possible. And then step 2 is to go to the source code relevant to that test. Now, because you're coding really slowly and carefully, and you're testing along the way, it's really easy to do that. Because if you wrote 200 lines of code, and then you tested it 3 weeks later, it can be anywhere in that code. But if you just wrote 10 lines of code and now something breaks, well, you can be pretty sure it's in that 10 lines of code. And finally, go to the code and trace step by step what that code is doing. And only then actually try to fix something. And you'd be amazed. So many students, because so many students will come to me and say, "Can you debug this? I have a bug." I'm like, "I have no idea. You have like 300 lines of code. I can't debug that, or I don't want to." But instead, I'm like, "All right, well, just what's this code supposed to do?" And they step through, and half the time they're just like, "Oh, they made some little mistake." And by stepping through and realizing what the program's actually doing, they immediately will understand that it's violating their expectation about what it's going to do. Yeah.
Can I take a picture of the serial code of the lift? We're going to get it
Sure.
replaced.
Oh, thanks. Oh, you didn't have to come now, but yeah, thank you. Thank you. I think I can get this up. All right, so the goal here of any programming or any system building is to make the specification. Is to make the specification match the implementation. And so this terminology, specification, implementation, is that difference between what we think it's supposed to do, our expectation, and what it actually does. The implementation is your actual code. Specification is what you think it's supposed to do. Specifications can also be written mechanically as well, but for this class, they're going to be in our heads, they're going to be on paper. And so this gives us a way to frame what a bug is. A frame is a mismatch between the specification, what it's supposed to do, and the implementation, what it actually does. And this is kind of the job that you do when you're ever doing programming. So the professor gives you a problem to solve, or your employer, and you have to write code that solves that problem, that satisfies that specification. And so what you're really doing is you're kind of turning specifications into code. So the question is, how do we do that? How do we actually make the specification match the code? So the hard way is to try to just write all the code all at once yourself, and then check when it's done. So just like with the hair, that feels really easy, but problems snowball really quickly. So think about it. If you've just written 10 if statements versus 2 if statements, which one is going to be easier to debug? Well, 10 if statements has 2 to the 10 different combinations of paths through them. 3 only has 8. Yeah.
I'm sorry, could you show that last slide one more time, please?
Yeah. So all the slides, all the notes will be online, and the videos. Yeah, I'm recording as well, so there'll be lecture videos and stuff. Oops. Okay, so that's the hard way. And just to give you kind of a visual of what this looks like. So here's my specification, here's my implementation. Here's you, the programmer, with your laptop in the middle, and you're kind of converting that specification into an implementation. So if we start out by just saying, all right, let me take this entire specification and try to fill it in all at once, try to solve all of it all at once, and then just write code. So I code, writing code. And unbeknownst to me, I'm sort of inserting implementation bugs periodically that I may not be aware of. And now, when I go back to debug, I've got this entire implementation to try to debug. And these bugs may interact or hide each other as well. This bug may only be exposed once you fix this one. And so you just have a really hard search problem to figure out where those bugs are. So that's the hard way. Feels easy, but it's actually harder, I contend. So the easy way, which I also call the lazy way, because I'm lazy, I don't want this to be hard, I want it to be easy, is to start with a really small specification of the program, like literally hello world. So hello world is like a subprogram for write a move function or something. So hello world is like a small piece of that. So I write hello world because I know I can get that right. So this takes a little practice. You'll learn all sorts of algorithms and all sorts of programming instructions to help you do this, but it's like a divide and conquer approach. You take a small piece of what the program is supposed to do and try to program just that. So the benefit of this is you can't keep code in your mind, all the code in your mind at the same time. Linux is 20 million lines of code, but it's broken down into functions. So you might be able to keep a 10-line function in your mind to think about it. But trying to reason about that entire 20 million lines of code is impossible. So here's what that kind of looks like very loosely diagrammatically. So here's us, the programmers, and we instead take this specification and try to divide it into subproblems. And similarly, when we write our implementation, we take each one of these subproblems and implement only that subproblem, testing along the way. And while we do this, we still may have bugs. We still may have mismatches in our specification. But because we're testing along the way, we only have to look here. We only have to look in this piece of the program. So that's why when you write functions, you're actually doing this divide and conquer strategy. You're breaking the problem down into pieces that you can debug and test individually. So this is kind of graphically why this approach, this tortoise approach, leads to easier programming and higher productivity, I argue. Okay, so just to kind of beat a dead horse here, spend time early. This is like delayed gratification. Spend time now setting yourself up for success, setting yourself up for good programming, and save time later. Save time debugging. Stitch in time, save time. So breaking problems down takes some experience. There's a double-edged sword here of trying to kind of premature generalization, trying to organize everything before you started. There are some kind of formal approaches to doing this. There's a good paper by Nicholas Worth where he shows doing the 8 queens problem, breaking it down in this, what he calls stepwise refinement approach. One methodology for breaking down problems. You can also do things bottom up. There are test-driven development approaches. Lots of ways to do this that you'll encounter and learn about in your career. And last thing I want to leave you with is this 3 virtues of a great programmer. Oh, it's loading. Who's heard of the 3 virtues of a great programmer before? Nobody ever heard of this? Okay. So this was from Larry Wall, the author of Perl, which has kind of largely been replaced by Python, but it's a classic programming language. And his 3 virtues of a great programmer are laziness, impatience, and hubris. These may be a little surprising to you. You might think diligence or hardworking. But he puts laziness first. And it's not laziness like, I'm just not going to do it or let somebody else do it. It's laziness in that I don't want this to be any harder than it has to be. I want to find the easiest way to get this done. And that's what the tortoise is doing. They're like, I don't want to have to debug stuff. That's really hard. I don't want to debug 200 lines of code. I don't want to write hard programs. I want to write easy programs. So if I can turn the problem into an easy program or a set of easy programs, it's got to be a lot easier for me. And you're going to be faster. Impatience, so this is the speed part. If your workflow, your IDE is taking a really long time to build, or you have to switch windows and you have to use the mouse, that's going to slow you down. So the impatience virtue is the motivation to make things faster for yourself. That'll also make you more productive. And it'll make you more enjoyable. You won't have so much overhead in programming. And hubris, this one is the probably hardest to explain, but the quality that makes you write and maintain programs that other people won't want to say bad things about. Basically, are you willing to take your code and let other people see it? So a lot of people aren't, right? But if you think about it like someone else has to use this code, and almost all tech companies, it's going to be collaborative programming. You're probably not going to be working alone on a project. You don't want to be the person that broke the build. You don't want to be the person that always does bad code or breaks things, doesn't get things right. So that hubris is, I want other people to actually see this and use it, and I believe that my code will be good enough to use. I mean, of course, there's always doubt, and you want to fix things and maintain things, but have that kind of bravery to say, I did this actually working code, and it won't break. Of course, everything will break, but do the best possible thing you can. All right, so that's it for the lecture. Oh no, I have some differences here. But any questions? Any thoughts so far? All right, so I'd like to give a little kind of change log of my course. So I redesigned this course a year ago in fall, kind of did a dramatic redesign. And it got pretty good feedback. And I kind of tweaked it, kind of improved things last semester and got really good feedback. So I try not to, fix what isn't broken here, but I did some small tweaks here. So I kind of tweaked instructions, just ease the use of Git and version control. There's a lot of commands to learn, so kind of ease that. Did some other kind of improvements to instructions. Tweaked the content a little bit to kind of order things so that easier stuff comes first. Some of the projects and exercises are updated as well, so it's not just exactly the same as last semester. One really useful thing is we do automated grading, and in the past, we didn't give you the results of that, we just gave you the score, so now we'll be able to give you that via Git, via version control. We'll be able to give you the results. I changed the bonus structure a little bit, which I'll talk about when I talk about the syllabus. And let me see if there's anything else here. Yeah, so these are more like logistical things that I'll go over. And if you want to see the changelog from other previous courses, feel free to take a look at the notes. But now let's take a look at the syllabus. Okay, so this is System Software, COP-3402. We're Section 1, so hopefully you're in the right place. There are no labs or office hours this week. So if you have some issue and you really need to talk to me, send me a message, but usually like nobody comes in the first week. And labs, no labs in the first week. We have 2 TAs, Sanan and Donovan. These are my PhD students. Donovan will be doing the labs starting next week, and we'll have office hours starting next week as well. So I tried to have office hours every day between one of us. This is 3:15 to 2:15. I probably won't be able to stay much after 2:15, so if that office hours doesn't work out, I can change this over the semester. Can anybody not do any of these office hours ever, any week? Okay, that's great. It's the first time I've ever seen that. All right, so you can see the whole schedule here. The topics, are the same as last semester. So we're going to start out. We have our introduction today. We're going to start with tooling. So we're going to learn the command line. We're going to learn version control, which is also happening on the command line. We're going to learn about build automation. Then we're going to go into our first system software kind of low-level implementation section. We're going to learn just about the file system. So we're going to learn the basics of the file system, and then actually how to use the operating system's API to do file system stuff, how to actually manipulate the file system. Then we're going to do processes. This is kind of almost like an OS idea. So in OS, you'll learn about how the stuff is implemented, but for system software developers, we're going to be using processes. We're going to learn the theory of processes. This is what makes it possible for you to have many things running on your single machine. Your single CPU can run many, many programs at the same time. We'll have our midterm after that. There's one midterm. And then we'll go into our compiler section. So we'll learn like really basic fundamentals of compilers. And then we're going to build the back end of the compiler, which is the part that generates assembly code. And we're going to generate real assembly code, real Intel x86 assembly code that will run on Eustace or your virtual machine if you want to use a virtual machine. And so you'll actually integrate into like the real x86 Unix tool chain. You'll actually use the other pieces of the system software to complete your programs. And we'll have a really basic language that you'll translate into assembly. We'll do a little kind of security. We'll do some classic security stuff as an added part of the class. There's no tests on it or anything. And then we'll have our final. And yeah, that's the schedule of the course. Any questions, thoughts on that? Yeah.
Just so the due dates, I'm seeing like currently I'm seeing what the due dates are. It says college Gen 2, college Gen 3, and then I was wondering if you could update those or what are those just the due dates?
These are the due dates, yeah. So the way this table works, and there's notes at the bottom explaining this as well, is well, let me just go over the assignments and then it'll be clear. So there are these are the categories of assignments. There's homework, and so homework there is homework for every lecture, which I know seems excessive, but it's not graded for like exact correctness. It's graded for effort. So it's really meant to keep you like up to date with the course. So my kind of philosophy in class is like to not have both grading for correctness and grading for punctuality, because I didn't like doing that in college. So, but also I feel like you're sort of measuring your personality as well, rather than your knowledge. So homeworks are really kind of a review of the lecture. They're meant to be maybe an hour each on average. Some will be more, some will be less. And so there's a lot of them, and it's every lecture, but it's not graded for correctness. So make your best effort. Take a small amount of time to do it. It's worth 20% of your grade. So the way I organize this is each point of each exercise is 1 percentage point in the class. So it's really easy to calculate your current grade or project your grade. So if you miss half the homeworks, you get 10% off your grade. You will have a hard time getting an A. Okay, then there are exercises. These are like homeworks, but they're programming projects. And these are or not even programming projects. These are very simple projects. These are not hard. These are just kind of paint by numbers. You follow along, and you can turn these in late up to a certain amount with no penalty. So these are really to teach you some of the technologies we're going to use in this class. Then there are the programming projects. This is like the meat of the course. It's almost 50% of the grade. This is the where you're actually going to be implementing system software and compilers. But being the hardest part and being, not wanting to penalize you for just being a little bit late, these can be resubmitted any time to the end of the semester for a really, really small late penalty, like a 1 point late penalty for submitting these. Then we have a midterm and final. These are in class, in person, but via web courses. And then attendance. Attendance is graded in this class, which may be a little surprising or annoying to you. I never had attendance before, but many students actually suggested this to me, and I thought it was a good idea. But I have a way that makes this a little less painful for you. So first of all, it's only worth 4 points. So you could skip all the classes and have no attendance and still get an A in the class. But if you come more than 75% of the classes, you get a bonus. So in other words, if you come every class, you'll get, and you get everything else right, you'll actually get 102%. You'll get 2 bonus points just for attending more than 75%. So you see how this works? So you can lose points if you go under 75% attendance, but you actually get more than 4 points for more than 75% attendance. Make sense? Sort of? So I tried to make it so it's not like a super, doesn't hurt your grade. I don't want punctuality or life issues to completely destroy your grade. So I figure 70%, I kind of tweaked this number a little bit, but of course, if you have actual excused absences, that does not count for any of this. So I put this here somewhere for late policy. Yeah. So I make it clear that, of course, the UCF late policy still applies to all of this. This is just when you're have the option or ability to come. Okay, so I summarize this late policy here. So homework, which is not graded for 100% correctness. There's no late homework allowed for this because we go over it in the next lecture, and you're not graded for correctness. The exercises, these are simple paint by numbers, programming or system tool exercises. You can resubmit these basically up to a week late or more if the lectures go beyond, if there's holidays or something. And projects, which are the bulk of the grade and the hardest part of the course, you can always resubmit these. So you could submit it and totally tank it. You get 20% on it. You can resubmit that anytime up until this final resubmission date in December. You can resubmit it. You can resubmit it 100 times if you want. We may not grade it 100 times, but you can keep resubmitting it. Because we're using version control. So you just commit your code. It's got a timestamp on it. And each of these projects is worth 8 points. You'll get 1 point off for a late submission. Not each time, just 1 point total. So even if you completely tank it the first time and you resubmit it 100 times, you'll still get 7 out of 8. Kind of make sense? Any questions on that? So yeah.
Will we be able to, before the due date, resubmit?
You can resubmit, but we're not going to grade it with the full test cases. So I should say also as well that we give you half the test cases that we grade with and never release the other half. But they're related to each other. So we'll give you half the test cases so you can test on half of what we're going to test on. And then we're going to give you the full, after the deadline, we'll test with all the test cases, give you your feedback, and then you can resubmit as much as you like. And of course, come to office hours, you can get help, go to labs. Yeah?
I saw on campus there's a homework assignment listed for this week. Is that also due by next lecture?
So yeah, that's a good point. The homework one is also the academic activity. So that's due by Friday. It's not due Thursday. So I don't think I say this exception here. But that's really for the academic activity. So if you have financial aid and stuff, it's you have until Friday to do that. But all the other ones are due the following lecture. But there's nothing to go over. You really just log into Eustace and that's it. Take a picture. Because that's all a good thing to do it. But it's super simple. You just literally log into Eustace, take a screenshot. That's it. Because I needed something to submit. Because I just want to make sure everybody's set up with Eustace. So homework one should be really, really, really simple. Hopefully. And ask. Well, there's going to be. I'll go over the discussion board as well. So. All right. Any questions so far on the grading scheme? So I realize it's slightly complicated, but the philosophy is there's a bunch of stuff that's small part of your grade that's due regularly, but it's not graded for correctness. And there's a bunch of stuff that's really high value part of your grade, but you have lots of opportunities to resubmit very, very light late penalties so that you can actually fix things and turn them in and get a good grade if you work at it. And then finals and midterm, they're not super high value. It's 20% of the grade together. So the philosophy here is that, even if you like cheat your way through like homeworks and projects, you'll probably have a hard time on the midterm and final. So they are in person. We do proctor them. And so it'll be tough to get like an A if you just cheat your way through the projects, because we're going to ask about the projects. You're going to do coding and stuff like that. So that's kind of philosophy here that I use for this grading scheme. Questions on grades, assignments? Yeah.
Are these on web courses?
They're on web courses, but they're in person.
Okay, yeah.
Yeah, so we like check IDs and stuff, and there's a time limit, and yeah, we also will give paper exams too, if you need. Yeah. Yes, they'll both be here. Yeah. Yeah. Do you have a question?
Is there any Zoom option for labs?
For labs, no, I don't think so. I guess we could ask the TA, but we haven't done that before. Yeah, not for labs. I think people ask if you can go to other labs, like if the time doesn't work out. I think so, as long as the room capacity is met. I don't think that's an issue if like the exact timing doesn't work out. These classes, my lectures will all be recorded and put online. Yeah.
What language will we using for the programming assignment?
C. It's all going to be in C. Actually, the compiler will be in C++, but you won't have to do any of the C++ parts yourself. It'll be basically C. Other questions on? Yeah.
Instead of the Unix environment that you just use a virtual machine?
Yes. Yeah. So in the last semester, I required Eustace and Emacs. I didn't put up instructions yet, but if you're interested in getting a virtual machine set up, so I used to require a virtual machine, but like it kind of penalized those who don't have really fast machines or like the right hardware. So I used Eustace, but then that penalizes people who are doing stuff off campus. So yeah, this semester you can definitely use virtual machines. I can help you with this. We can go on the discussion board and help you set things up. So you could use WSL like Ubuntu on Windows. You can install your own virtual machine, Docker, Vagrant. But the main thing is double check it on Eustace, because we're going to be doing all of our grading on Eustace. And Eustace was just upgraded to Ubuntu 24.04, if that means anything or matters to any of you. So I'd recommend getting a virtual machine with that OS. Yeah.
Do we have to use Emacs, or we literally?
No, you can use other. So last semester the previous year I required command line text editors, and I think that was pretty painful for people, particularly those who chose Vim. Who's ever heard of Vim? Some people have. So some people chose it. They were new to Vim, and I think it was pretty rough. Even Emacs. So sure, you can use any editor you like, but just make sure it builds and runs on Eustace. So a lot of people in the past would use VS Code, and there's a lot of bloat if you're using remote connection with it, and people would run out of disk space. So you may go the virtual machine route, maybe with VS Code if you're comfortable with VS Code. And I think I had Emacs as a requirement. I had it as a requirement, but all the instructions for using the command line will be done with Emacs. So it's good to know some text editor in the command line, because there's things that are much easier to do on the command line if you just have a text editor. For instance, writing commit messages for version control. So the first reading that I have is the Emacs tutorial. And you can actually do this right on Eustace, right in the Emacs editor if you just run these commands. And I show you how to exit Emacs. So this way at least you won't be totally lost if you, I would recommend doing this, because when you're in Eustace you have no graphical interface. So you'll be sort of have to use Emacs at certain points in the class. Oh yeah, I should also say that there's reading. Oh, yeah, any other questions about logistics? Yeah.
Mine was more about the textbook.
Oh yeah, I was going to go to the next. Yeah, go ahead.
For the 21st century C book, I can't find the first edition anywhere. I can only find the second edition.
These are free to UCF students, these books. So if you click on these links, you'll get, they should be free. So the libraries were really, I can't do this right now, but the libraries were really great about getting access to 21st Century C. There's some instructions here. You should download the chapters. Don't read online. I think They might have since corrected this, but if you do that, you're going to like block everyone else in the class from reading it or something. They have like a weird license. So don't do that. Your institution has access to one copy of the book, apparently. So don't do that. Don't be that person. And it does link to your name, so to like kind of give you some shame protection against doing that. But just download the chapters. And there's a limit on how much you can download per day, but if you just download these, it's within the limit, or at least it was last semester. So it's free. It's free. I try to not have any textbooks you have to buy. Yeah.
Don't read online?
Yeah, don't click read online. Read these instructions. So these are the instructions that were given to me by UCF libraries because they had like access to one copy. You can instead go down here to download PDF. Yeah.
Where are these links at?
This is on the syllabus. This is all on the syllabus. So if you go to the syllabus, table of contents, you can see textbooks here. So yeah, I recommend, it's kind of long, but I recommend just going over it, reading over it. Because I try to be like comprehensive in everything you need for this class. So logistics. Any other questions on this stuff? Yeah.
If the exams are on web courses, wouldn't it be easier to take them at the testing center? Is that correct?
Maybe. You mean is there, yeah, that'd be great. How do I do that? Is there a testing center that yeah, that would be useful. All right. Oh, okay.
You go there and then they walk you down. You can only access.
All right, let me take some notes on this. So I knew that was possible for SAS students. I didn't know there was testing center. I feel like I looked into this before. All right, before taking the test. So there may be too many people or something. All right, yeah, I'll look into that. If we can do that, that would be great as well. Yeah.
The issue with that is that there should be around 500, especially if everyone's doing the same time. It's mismatches. So when I was taking Portuguese, I had enough time for my schedule. But I also didn't.
Yeah, I think I may have looked at it. There's some other student might have told me about this, and I think that might have been the issue was scheduling. So, yeah, that's why we have it in person. So I used to do all paper tests, but kind of turning 2 pages to 200 tests, that's you're just physically doing page turns is 10 minutes of turning pages for grading stuff. So I switched to having web courses in person, which does seem kind of counterintuitive, but it's really just to help with grading. And I still will print out some paper tests for those who don't have a laptop or the laptop dies, or they just want to do it on paper. But I'll look into it again. But I think scheduling might be the issue with 200 students, 210 students. Yeah.
For attendance, is it just a QR code we scan?
Yes, attendance will be UCF here. So let me go through. Yeah. Go ahead. I don't. No, we won't do attendance for labs. Okay, so let me go over the logistics of the course, kind of all the mechanisms I use in the course. I know this is a lot of stuff, but I'm trying to be really comprehensive here. So these are all the pieces of the course that you need. Everything is free and online, except a machine, that you'll need a machine, which also there are free options, which I'll show you. So syllabus is here. This is all the kind of information, the main information of the course is on this syllabus webpage, which you can access from web courses. The very first thing in web courses here is the link to the course webpage. And there's also a sidebar here. So this is kind of the authoritative information. This is where you'll look for all the information about the course. Lecture notes and videos, they'll also be linked from here. So all of my slides, I turn them automatically into lecture notes using Emacs, actually. So I use Emacs technology to do this. That'll be on the website. Videos will be recorded on YouTube. That'll be linked from the website. Homework assignments will be linked from the website. I've also copied them into web courses because some students prefer that. Project descriptions, also on the website. So all this stuff, just go to the website for all your needs, information about the courses. Yeah, so I should say homeworks you submit them on web courses, but all the programming projects are done via Git. So project implementation, I say Eustace here, but you can use a virtual machine, but you're still going to need to test it on Eustace, or you should, so things don't break. Project submissions are going to be through Git, and that's going to be part of the course to actually learn how to use Git and how to submit stuff. Homework submission is on web courses. Exams are in person on web courses. I'll go to details later about that. And we're going to use Ed Discussions, or Ed STEM. Has anyone ever used this site before? It's yeah, it's like a discussion board. We're going to be using that for this class. And attendance is with UCF here. So you'll need access to a computer for this class. But if you can't afford a computer, you can't afford like a $3,000 Mac or something, there are computer labs. I know that's probably not the most desirable but everything's on Eustis. So you can go to a computer lab on campus. You can connect completely free. You don't need a device. If you don't know already, the libraries have loaner devices, so you can actually borrow a laptop. And if you don't need a computer the entire time you're coding, because if you're like the tortoise, you'll plan things out, you'll do comments, think of test cases. And also, I want to point out, and I wanted to do this for class, but I've been too lazy to get around to it. But you can literally go on a marketplace website and get a laptop from 10 years ago, 15 years ago, for like $50, $80, $100. You can get surplus from UCF. So really nowadays, it's pretty achievable, I think, for everybody in the US at least, to buy a laptop, because in this class, everything's on the command line. You don't actually need any graphical stuff. You don't need Mac OS or Windows. You can just install a command line Linux. It'll be insanely fast on 15-year-old hardware. You can get a Chromebook, which is really cheap. You can also connect to Eustis from a Chromebook and do all your development there. Internet connection might be an issue if you're off campus, but yeah, you can really, really cheaply install a Linux distribution. If anyone's interested in this, let me know. I can help walk you through it. It's pretty easy to do nowadays. You can install like Ubuntu 24 from a USB flash drive, and voila, you've got completely free operating system on really, really cheap, slow for running video games today, but fast for Linux. Individual cores of processors peaked, like 10 years ago. So Intel, they just do like multi-core to make things faster. So you can get a 10-year-old laptop that's going to run the programs in this class extremely fast. Just want to say that. Has anyone done this before? Bought like a really cheap laptop and installed Linux? All right, that's cool. Okay, we got some people who've done it. All right, okay. So let me know. If you're having trouble with your current machine, or you want to you don't have a machine, let me know. Okay, so we'll be using Eustis. Who's not used Eustis before? Oh, some people haven't. Okay, so some people haven't used it in the course. So it's just a Linux server. So you connect via this address. On your local machine, you'll have to connect via SSH. Now, the way to do this depends on the operating system you have. So I've got guides here. Let me know on discussion board, or email me. Let me know on discussion board. Don't email. Let me know on discussion board, which I'll set up. Yeah, I'll have to set up this week. If you add and drop, I may need to add you again. But you can ask on the discussion board if you have any issues doing this. But there are guides here for each of the main operating systems for doing this. Yeah.
Is Eustis available yet to people who haven't had access to it? Because I'm having an issue using my credentials, and another professor told me I'd have to wait till after the ads are activated.
I think the department told me people should have access already. If you're already registered for the course, you should have access.
Okay.
Yeah, let me know if you don't, especially if homework 1 you can't complete or something. But I think everyone should now have access. I think they told me that. I think they had the admins. I'll check my email again, but I'm pretty sure they said people should have access. Has anyone tried logging into Eustis this semester? Okay, so some people have. You might have access from like last semester or something. And there's a nice guide from a former lecturer here, Solansky, about using Eustis. Okay, so that'll be homework 1, is like connecting to Eustis. This will also help flesh out any problems we have if everyone's not added yet. It'll be quickly apparent. But this semester you can also just use a virtual machine. But you still need to connect to Eustis. It's still part of the homework. It's still where you want to run all your tests and everything. I don't have complete guides for all this stuff, but you can let me know if you're interested. So if you want to, say, use Git from your local machine, you kind of have to use Git on Eustis right now, but there are tricks. It's a trick called proxy jump, where you can basically hop through multiple machines to get to the Git server. Programming projects will be submitted as Git repositories to this server. I'm going to give you instructions. There's going to be the first exercise you do is going to be like a step-by-step guide to using Git and submitting projects with Git. So don't worry about that right now. Web courses. Hopefully everybody knows web courses. Anyone not used web courses before? Okay. Ed discussion, so this is going to be our discussion board for this class. The site looks like this. I haven't added anyone yet, but I'll add you guys soon this week. So you could send me emails, but my inbox is pretty horrendous. So EdSTEM is something I'm going to check, and the TAs are going to check regularly. So you're much more likely to receive a response if you send on this board here. And you can send private and anonymous messages as well to either only the staff or everyone if you like. So you can preserve some anonymity if you'd like to. And then UCF here. Has anyone not used UCF here before? Okay, most people have. Okay, so yeah, you need a device with a camera, like a mobile device. If you don't have that, or you're not willing to, or you don't, you're concerned about privacy, or you don't like having a mobile phone, I think you can use a laptop with a device as well. Has anyone ever used a laptop with a camera to do this? I think people in the last semester said I had. But let me know. Let me know if you don't have the facility or the desire to have like a camera-enabled device. But if you have a cell phone, you can just do this from your cell phone. So yeah, we'll pop up a QR code. You'll put your point your camera at it, and then it'll mark you here. All right, textbooks. So as I said, these are free for UCF students. So you'll log in with your, you'll click on this link here, and you can log in using your UCF account, and you'll have these books for free. So just download the chapters, as I said before, and there you go, free textbook. Yeah.
Sorry, did it say that UCS is only accessible while we're on campus?
No, you can use the VPN. Did I say that up here? Yeah. So off-campus access, yeah, campus or VPN.
Can we use that VPN, or can we use like your VPN?
No, that VPN. So that VPN will pierce the firewall that UCF has to prevent people from the outside from accessing UCS. That will give you a tunnel into the campus network. Has anyone not used the VPN here before?
Is it Cisco?
Yes. Yeah, the Cisco VPN.
Well,
Yeah.
can we kind of download it and everything?
Yes, this gives you instructions for it. So this should be the instructions. Let's see if they're still here. And this website, you go to this website, and it'll walk you through downloading. Some students did have problems with this in the past. Some students, if you had like custom network settings, you might mess this up. That might mess things up. There were, I think, some people in off-campus housing was getting blocked. The VPN was getting blocked in some off-campus housing. I don't really know how to resolve. I mean, there are ways to resolve that, but like kind of less legitimate ways to do it. But
You can use OpenVPN and use that configuration as well.
okay,
If you don't use Cisco.
okay. Yeah, let me know if you're getting like blocked by your housing firewall, which is insane. But then in that case, you could use like a virtual machine, and then when you're on campus, you could submit then. Other questions on logistics? All right, so those are the textbooks. They're free. These are the chapters to download. You should be able to download them all in one day. It shouldn't exceed your limit. There are detailed instructions here. I've got some optional texts here. These are not required for the course at all. But if you're interested, particularly in like programming and compilers, these are some really good books. This is the Emacs tutorial, which is the first reading of the class. Go through it until you're tired of it. Don't spend like 3 hours. I think it's only like an hour, but you don't have to do the whole thing. But I'd recommend just going through, learning the basics of these commands. It'll be useful to have command line editor. If you're sort of in the command line kind of nerd culture, there's a big war between Vim and Emacs users. I'm an Emacs user. My students Vim users, and you can also learn Vim if you like, if you want to do the command line. It's a kind of a little bit harder tool to use. All right, we've got some good references here for Git and Emacs, and that's it for the logistics of the course. So this is kind of the common information about the course and policy statements. So read over these for sure. They're probably going to be similar to what you've had before. And that's the syllabus. That's the organization of the course. So questions about the course? Yeah.
For the last, I know you said there's no attendance, but is there a way to make up the class?
The lab course? No, not really. They're kind of live and in person. They're really for kind of answering questions. They're kind of like a group office hours. Yeah, it's like a recitation. It's like a recitation. Other questions? Yeah. No attendance this week. I want to take it because the ad drop period, so I won't do attendance this week. Other questions? All right, other questions, you can come up and talk to me. The class has decided it's over, so.